life in the Earth, despite the fact that the deeper you go, the higher the pressures and the higher the temperature. But its life is very small. It's microscopic organisms, mainly bacteria. And these organisms can survive those conditions. In fact, some can grow at temperatures as high as 113 degrees centigrade, much higher temperatures than boiling water. The startling thing about life in the subsurface is the first estimates of the total bacterial population there indicate that they represent about 70% of all bacteria on Earth. So the majority of bacteria actually reside in the subsurface. They're not in this thin veneer very close to plants and animals we're used to.
But what do bacteria find to eat down there? New discoveries suggest it may be the Earth itself. In Verne's day, science believed that all caves were created by water, wearing away the rock. But is this right? These caves were formed millions of years ago, before the sea level rose. Now they're only open to intrepid diver scientists like Sam Smith. She believes it's not water that eats away the rock, it's bacteria.
I think that without bacteria, caves and limestones would not exist. You really do need the bacteria to form carbonic acid or other acids in the soil zone above where the caves might start to form or develop, which then starts to carve out the cave. There's no doubt that over time, water corrosion also plays a role, but bacteria need to be there as well.
Microbes or meteors? Join our teams of scientists as we go deeper still, searching for clues about what formed the Earth. Sam's study site is in the Yucatan Peninsula in Mexico. The caves extend for 50 miles and are up to 400 feet deep. If Sam is right, rock-eating bacteria hollowed them out, and they're still at it. The quest for the bacteria takes her deep into the underwater maze. This is a dangerous place. Sam's exploration is at the limit of diving technology. There are only 3 scientists in the world experienced enough to dive into caves this deep. All their equipment has a backup, or even 2, since problems must be solved on the spot. This is no place to get lost with your air running out. When Sam finally gets to a spot where the rock-eating bacteria could be at work, she makes sure the samples she collects will be perfect.
To take our samples, we use 10-meter length tubing, silicone tubing, that basically allows us to take a sample at a point 10 meters upstream of us, and it minimizes the diver's disturbance to the water, so that sample is as sterile and as clean as possible.
Having come this far, it's vital that Sam doesn't contaminate the samples with her own bacteria. Only then can the return journey begin.
After we've collected the samples, we immediately take them back to the cave surface where they are put on ice right away and kept on ice until we get them back to the field lab.
The bugs are cooled to 40 degrees and flown in this standby state from Mexico to Sam's lab in England. It takes about 8 hours. A Jules Verne hero managed to race around the world in 80 days. It was 10 years after Verne wrote Journey that Louis Pasteur put bacteria on the map. And for another century, the world would see bacteria as a nuisance. Now, scientists like Sam suspect they may become a vital and inexhaustible commodity. First, she wants to know how many rock-eating bacteria there are. She wants to know if they're all the same type. Most of all, she wants to verify that the acids they produce can carve out caves. If Sam's right about these microscopic miners, it's a giant step forward for geology.
It's something that's quite exciting to think that something so small, so the bacteria, which are about a micron in size, so 1/1,000,000th of a meter, can actually alter something so large or have such a large impact on the environment around them. Bacteria exist everywhere, in the air, in water, land, sea. And anywhere we've looked for them, so far we've been successful at finding them.
So, will we find bacteria at the center of the Earth?
If you want to think about how deep we could go and still find bacteria, it probably is temperature dependent, but we haven't reached that maximum yet. We haven't looked deep enough yet where they haven't been there.
Because they can eat what we can't eat and thrive in conditions we find extreme, bacteria may turn out to be the Earth's real buried treasure. They're already at work in our homes.
We all are used to using biological detergents in washing powders. These come from organisms that can grow at 60 degrees centigrade. If we can get organisms growing at 130, 150 degrees centigrade, basically they could make superb catalysts for a whole range of different compounds.
Unlike some other resources, there's no shortage of bacteria. This core sample of rock comes from 200 feet below the surface. It contains as many bacteria as there are people on this planet. We've come up with bacteria wherever we've drilled, and however deep. They can survive for millions of years, buried alive, without food or oxygen. Some see them as an infinite, untapped labor force. The first oil wells came online in Verne's time, but the era of easy-to-get-at fossil fuels is almost at an end. Unless these new microbial workers can help us out.
We know that we leave something like 40% of all the oil in reservoirs in the ground. We can't extract it. And for example, if we're able to manipulate these deep organisms, they might be able to convert the oil into gas, and then several years later we could come back and we've got a viable gas field instead of a spent oil field.
Verne's adventurers didn't strike oil, but they did find platinum and gold. They decided these were too deep ever to be mined. Verne meant by men. He hadn't reckoned on microbial miners. The idea of using microbes to extract minerals was beyond even Jules Verne's imagination. But because some types of bacteria digest rock, they're already being used to separate metals from ore. And that's just the beginning. One day, we'll be able to put bacteria to work at depths we just can't tolerate. Until then, we'll go on doing it the hard way. Mining at 12,000 feet is difficult, dangerous, and expensive. Every mile you descend, the Earth gets hotter by 50 degrees. The mine uses more electricity than a small city, making 80,000 tons of ice a day, and lifting 10 tons of ore 2 miles to extract each and every ounce of gold. It's the rock's history that lets us mine here this deep. Most places would be simply too hot, but in South Africa, the Earth's crust is older than in most other places, so it's had more time to cool. 2.5 billion years ago, the gold accumulated on the surface in a lake. Over time, the land and the gold was tilted and forced down into the earth. No richer deposit has been discovered. Three-quarters of the world's gold has come from it, but that's only 2,000 tons. To find out why metals like gold and platinum are so rare, we must go back to a time when the whole of the Earth was molten. $4.6 billion years ago, a continual rain of meteorites pounded the molten Earth. Each strike brought with it more rock, making our planet bigger and scattering metals over the surface. Then, a giant asteroid struck. Its massive iron core didn't stop on the surface. It sank towards the center, and it attracted all the Earth's metals to it as it went. The asteroid's lighter, rocky debris went spinning around the Earth. The fragments were drawn together by gravity. Within a year, they formed our moon. That's why the moon has no metal at its core. And it's why metal is rare in the Earth's crust. It arrived much later, in meteorites from outer space. If we want much more metal, we must go to the Earth's core. It's made mostly of iron and nickel, but 1% is gold. That may not sound like much, but the core is so vast that its gold could cover all the land on Earth, knee-deep. In South Africa, the miners are already going deeper in search of more gold. They plan to follow the seam to 3 miles down, where keeping the mine cool could account for 20% of the mine's outlay. They may need temperature-controlled suits or robots to extract the precious metal. The northern and southern lights, beautiful and benign. But what will happen when the lights go out? In 1860, no one really had a clue what went on 4,000 miles below their feet. Many people still believed that the Earth was hollow, a theory put forward 200 years before by the astronomer Halley of comet fame. In 1823, an American, John Cleves Sims, had led an expedition to prove that Halley was right. He didn't succeed. Jules Verne knew of Sims' theory and kept an open mind. But he led his explorers into an immense underground cavern in which they had to cross an ocean lit by lightning and magnetic storms. This was pure fantasy. But the scene also drew on fact. Verne's research had convinced him that traveling down into the Earth would be like going back in time. So the creatures stirring in the deep were real. 200 million years ago. Plesiosaur. The first remains of the long-necked reptile were found in 1820. The dolphin-shaped ichthyosaur, unearthed in 1809. Verne was right. There is an ocean at the center of the Earth. A tempestuous sea of molten iron. As this surges in turmoil around the solid inner core, it generates magnetism. A colossal force field stretches into space, protecting us from solar radiation. Sometimes we can see it. The northern and southern lights put on a show when electrically charged fragments from the sun collide with the magnetic field. But there's evidence that its power is fading, and that could mean we'll be exposed to a lethal dose of cosmic rays. At Harvard, Jeremy Bloxham is trying to find out why this is happening.
One of the goals of our research at the moment is to try to develop a capacity to forecast what's going to happen to the magnetic field in the future. And this is of particular interest at the moment because over the last 150 years, we've seen the strength of the field decrease by almost 10%. And that's a rate of decrease which is characteristic of the field heading into a magnetic reversal. So an interesting question is, will the magnetic field actually reverse?
A magnetic reversal, or flip, means the North Pole becoming the South, and vice versa. Compasses will point the wrong way. Navigation will be literally turned upside down. But this won't be the first time it's happened.
There's been maybe 60 reversals in the last 30 or 40 million years. So in geological terms, they're a very frequent event. Just in the timescale of human experience, they're a very rare event.
But what will happen in a flip? Will we be able to find our way around? Today, magnetic compasses are used less for navigation. Instead, we use GPS satellites, which won't be affected. But before the flip, the Earth's magnetic shield will fail. And without it, satellites bombarded by radiation will burn up in space. It's not only human navigation that will go wrong. Many animals rely on internal magnetic compasses for migration. But no one knows how they will manage. But flips don't happen overnight. The force field fades slowly. Jeremy Bloxham is watching it closely.
There's a variety of techniques which we can use to see how the field is changing. We have modern measurements from spacecraft which are in orbit specifically to measure the magnetic field. We have permanent magnetic observatories set up at various locations around the world which continuously make measurements of the magnetic field. But measurements like that only tell us what's happening on a timescale of decades to perhaps a century for the longest running observatories. But the magnetic field is changing on much longer timescales, so we need to be able to ask, how can we find out how the field has changed over centuries?
Fortunately, navigators long depended on the magnetic field, and we've learned a lot about its variations from their charts. And the changes continue. Today, magnetic north is leaving Canada and heading across the Arctic Ocean at a steady 10 miles a year. But it's one thing to know the poles are moving, another to know why.
The Earth's core is liquid iron, or mostly liquid iron, and the motions of that electrically conducting iron can create what we call a dynamo. But the details of that process, how it actually works, are still very poorly understood.
To understand it better, Dan Lathrop has built a working model of the Earth's core.
We've been building a sequence of experiments, progressively larger and higher powers, to try to get the same parameters as occur in the Earth's outer core and try to understand how the Earth generates its magnetic field.
Keep an eye on the temperature, too.
We like to know what sets how strong the Earth's magnetic field is. We also would really like to understand what causes all of the changes that are seen, anomalies in the field and reversals, and to be able to both understand what causes them and be able to predict them.
The floor of the Atlantic Ocean bears witness